Hello everyone. Good evening. Thank you for joining in. I am Hetankshi Desai and I would like to welcome you all on behalf of Women in Data Science Mumbai team to our weekly Tech Talk series. So, with Women in Data Science, which is a Stanford initiative happening at global level, we have conferences annually. It has been spread across 150 plus cities, 60 countries, reaching out to more than 1 million participants worldwide. The agenda of which is inspire, educate, and support to all the women in the field of data science, data analytics, statistics, mathematics, machine learning, artificial intelligence. The conference is generally driven by all the women speakers throughout the world, happening in different parts of the world. So, for the WITS Mumbai conference, it first started in 2018 in VJTI with 8 speakers. 2019, DJ Sangvi with over 9 speakers. And because it is not possible for us this year to hold a conference, we have done it a YouTube online series with almost 12 speakers so far. Today we have our 13th speaker. It's a weekly webinar series. These were the topics covered in May, June, in July, and today we have the sessions on recommendation system. These are our handles. You can go through the channel of which Stanford, which Mumbai on YouTube and other platforms. They have also started with a podcast series on Spotify. We are not really sure about the name, but then we'll be revealing it soon on all the different handles. Today, we have with us Gunjan Dewan. She has done her BSc Honours Mathematics from Jesus and Mary College. She has done her MS in Data Analytics from Shiv Nadar University. Having an experience of over 3 years in the field, working as a data scientist, currently working at Gojek. So, welcome Gunjan.
Hi, thank you.
Hi. So, about Gunjan, I would hand it over to Gunjan.
Thank you so much, Hetankshi. Thank you so much for that introduction. It's an honor to be here today, and I've gone through some of the WIDS Mumbai series that have happened till now, and they have been absolutely amazing. And I hope that today is up to the mark according to that. This is technically my first talk that I'm giving to a bigger audience. So I'm honored to have this opportunity. And should I start? Should I share my
Uh,
screen?
yeah, just a quick note for everyone. If you all have any questions, please drop it in the comment section and we will take it up at the end. Over to you, Gunjan.
Thank you so much. Well, hello and welcome to my presentation on developing a matchmaking algorithm between customers and products. So a little bit about me. I have a background in mathematics with a master's in data analytics, and I've been working in the industry as a data scientist since the past 3 years now. I am also currently an industry mentor at springboard.com, and I'm currently working as a data scientist at Gojek, specifically for GoPay fraud. I'll start by talking a little bit about Gojek and what we do. Gojek is a super app. It is 20 plus services all in one app, starting from ride hailing to food delivery to getting a massage, booking tickets, paying your bills, you name it. All of these services are there in one app. And we also have a payments platform or a payment wallet called GoPay. Gojek is Indonesia's first and fastest growing decacorn, with its headquarters in Jakarta in Indonesia. We are spread across 207 cities in 5 countries in Southeast Asia. This is what I will be covering in my talk today. I'll start by talking a little bit about customer targeting. Then I'll move on to talking about the problem statement that we were trying to solve. Then I'll talk about the iterations that we took while solving this problem. Then I'll talk about the challenges that we faced and how we overcame them. I'll finally conclude by talking about the workflow that we currently have in production and what our field test results look like. Let's say you start a business to sell homemade chocolates in your local grocery stores. And you want to send an email blast to your network to publicize your business and to get people from grocery stores to want to keep your chocolates in their stores. Would it make sense for you to actually go and just send 10,000 emails to everyone in your network, especially if you're paying for each and every email that you're sending? Or would it make sense for you to carefully target the emails that you're sending to people who are most likely to be interested in your business and who would help you in moving forward? I'm pretty sure it's the latter. And that's exactly what customer targeting is. Customer targeting is finding the right set of people to target for any marketing campaign that you want to run. For the purposes of this talk, let's define customer targeting as, given a voucher or a promo, we want to find the set of customers who are most likely to redeem that voucher. Now let's try to understand this better using a diagram. Let's say you have a universe of all Gojek customers. Now out of this universe, there would be a base pool of customers who would be eligible for the promotion or the campaign that you want to run. Let's say we want to run a campaign to get more and more people to convert to our food delivery system, which is GoFood. Then our base pool will consist of people who have never transacted with GoFood but are there in our Gojek universe and have transacted with other services. Now, out of this base pool, we would want to find a targeted set of people who would be most likely to convert into GoFood. Now, let's say you have 1,000 people on your platform, right? Out of those 1,000 people, let's say 500 people actually use GoFood, and the remaining 500 have used other services but have not used GoFood. Now, out of those 500 people, it is not necessary that all of them would be interested in using GoFood in the future, right? Now, the problem of customer targeting is to find the set of those small 100 people who are most likely to use GoFood in the future. Why do we need it? Well, you get better conversion rates at lower costs. Let's say, like I said, if you have 1,000 people in your platform and you send a voucher to all 1,000 people and say 10 people convert, you only have a conversion rate of 1%, whereas you've spent on generating a campaign for 1,000 people. Whereas if you would have only taken top 100 people who would convert and sent the voucher to those, and 10 people out of that convert, there you have a conversion rate of 10%, and you're also spending less because you're only sending that campaign to 100 people. What we are facing is something similar. With so many products at Gojek, a natural question that pops up into our mind is, do all of our customers use multiple products? Let's take the example of a person, Mike, who uses our food delivery system and pays using GoPay for it. But he's never taken a ride or a car ever in his life. Does it mean that he will never use it? Or let's take the example of another person, Indra, who uses car and ride on a regular basis, but has never used our bills payment app Go Bills. Does it make sense to send her a voucher to see if she will use it or not? With so many active users and so many services, the permutations and combinations are endless. But the key point is that for us as a business, it makes sense if more and more of our users use more and more of our services. That's why we decided to build a algorithm that helps us do effective targeting. We devised a matchmaking algorithm for targeting cross-selling of products that users weren't familiar with. Now, what does this mean? What does this term cross-selling mean? Cross-selling is basically, okay, let's take the GoFood example again, right? Where we are trying to convert more and more people to using GoFood. There, we're trying to take a set of people who have never used GoFood and convert them into GoFood users. So we're cross-selling them to becoming GoFood users. Let's say a person uses GoRide and we want to cross-sell them to use GoFood. So this transfer or this cross-selling of a user from one service to another is basically called a cross-sell model. And for a cross-sell model, your base pool would comprise of people who have never used the service in question, but they have used other Gojek services. So the formal problem statement boils down to this. Of all the users who have never used a service, find the subset that is most likely to use it when introduced to it. Now, our first hunch to solve this problem was using a classification model. A classification model is simply a model that helps you divide your data set into 2 or more classes if such classes exists. Now, customer targeting is a classification problem because what we're doing here is dividing your base pool into 2 classes. People who will redeem the voucher or people who will cross-sell, and people who will not redeem the voucher or who will not cross-sell. Now, even though this approach was working really well, it was giving us around 5x uplift on one of our key services, there were certain problems with this approach. Now, like I said, right, the base pool of a cross-sell model is a set of people who have never used the service in question. Now, as we change the service, the base pool itself will change every time we want to run a new cross-sell model. So we need to train a different model for every voucher. And the base pool and the features will be different for different vouchers or different cross-sell campaigns. So scalability was a huge issue for this particular model. We could not practically scale this if we want to use this model across all our products at different points in time. So we needed a model which was generic enough and was giving us good results. At this point, we realized that we need to maybe rethink the way we were looking at this problem. We changed our perspective and we started looking at it as a matchmaking problem. Now, what do I mean by matchmaking? Let's say we have our customers on the left side and we have our services on the right side. What we need is an algorithm that simply, given a customer, tells me which are the services that this customer is most likely to use next. And at the same time, given a service, tells me a list of customers who are most likely to use that service next. So the idea is to build this kind of a model. So if we have something like this, it will be generic enough to such that we don't need to do a lot of rework. We don't need to put in a lot of effort to use this across services. I'm going to take a pause here and just check if there are any questions yet. Okay, so there are some questions. Can you explain if, the question number 1 is, can you explain if I want to target whom to send the message to provide loan from bank? So that's a very specific question and it will be a little difficult for me to answer that exactly. Can you explain if I want to target whom to send a message to provide loan from banks? So the point of this this talk is not to give you a set of people to target. It's more about how you can devise an algorithm to build a targeting model. So let's wait till the end of the presentation and see if you get your answer. All right. So like I said, we need to build a matchmaking algorithm now. Now for this, we thought about recommendation engines. Now, recommendation engines are probably the most relevant algorithm that is there out there in today's world. When you see ad on Google, which is very, very relevant to you, or if you see a show on your Netflix homepage, which you've been thinking about watching the entire day, or if you see a very, very relevant product to you that you've been thought of buying on Amazon, all of these things have a recommendation system sitting behind it. A recommendation system uses users' history and users' past purchases and behavior to predict what the person is most likely to predict in the future, to purchase in the future. We are using recommendation systems as a matchmaking mechanism between users and services or payment methods. We are treating each service as an item in the recommendation engine based on collaborative filtering. Now, I'll go a little bit into detail into all of these terms and what I meant by everything I just said. Now, every recommendation engine based on collaborative filtering has a utility matrix associated with it. A utility matrix is simply an N cross M matrix that captures the interactions between users and items. Now, these interactions can be anything from browsing history to purchase history to click patterns to even ratings that a person would have given to a particular item or a movie or a show on Netflix. This is what a sample utility matrix would look like. Each column would have an item that you want to recommend, and each row would be a user that you want to recommend to. And each cell here will be filled in with a particular number if there is any interaction between user and item. Now, the cell here is filled with 2 because let's say probably user 1 bought the item 1 twice. And a cell will be empty if there is no interaction between a user and an item. So the cell between user 1 and item 2 is empty because there has been no interaction between these two entities. These are some properties of this matrix. The values that you fill in these matrix could be explicit feedback or implicit feedback. And one very important property of this matrix is that it will be very sparse. By sparse, I mean that most of the values in this matrix would be missing. Why would that happen? Well, you might have a lot of items and you might have a lot of customers, but not every customer would be using or interacting with every item. Now, every time a customer is interacting with an item, you will find a value there. But every time he or she is not, you will not find a value there. So that is why, in a larger sense, this matrix will be very, very sparse. Now, in the end, the problem, our final goal should be to predict or to fill in the missing values that are not there in this utility matrix. Now, imagine if I'm able to figure out what this cell should be filled with, if I'm able to figure out what interaction should be there between or is most likely to be there between user 1 and item 2, I will be able to figure out if I want to recommend item 2 to user 1 or not. So our final goal is to fill in or predict the missing values of the utility matrix. Now, this is what a generic utility matrix looks like in a recommendation system engine scenario. Let's have a look at what our utility matrix at Gojek look like. So each and every service and payment type combination was represented as an item in the recommendation system. So each of this is one column. Now, let me elaborate a little bit on this. When I say each service, it can be something as vast as GoFood or GoCar, that you want to run a campaign for targeting people to convert to GoFood. So you would have GoFood as your column. You can also have something like a combination between GoFood and GoPay, which is our payments platform. Now, when a person books a GoFood order, they have an option to pay via cash, or they have an option to pay via our payments wallet, which is GoPay. So we can even have GoPay, GoFood as one column here, which would help us target people to convert into two services at the same time, which is GoFood and GoPay. And each row is representing one customer, and the cell between a customer and a service is filled if that person or that customer has transacted with that service in the past 1 month. So let's say user 1 has transacted with GoFood thrice in the past 1 month. That's why there is a 3 here. Whereas user 1 has only transacted once with GoPay offline in the past 1 month. That's why there's a 1 here. Now, user 4, on the other hand, has not transacted with GoFood in the past 1 month. That is why the cell here is empty. And this is exactly what we need. To remind you, a base pool for a cross-sell model is the set of people who have never transacted with the service in question. Now, each missing entry here represents the base pool of the particular service, which of the column which that service belongs to. So all the missing values under GoFood actually represents the base pool of GoFood to target for GoFood. Similarly, all the missing values under GoCar represent all the base pool for a targeted campaign for GoCar. So if we're able to figure out how to fill in this particular utility matrix, we're actually solving the matchmaking problem that we had devised a while back. Because given a service, we are able to find a list of people who are most likely to cross-sell into that service by using the columns here and after finding the missing values. And given a customer, we're able to return the services that the person is most likely to transact with next using the rows that are here. Okay, I'm going to take another pause to see if there are any questions. Please feel free to ask any questions. You can explain recommendations to group of people. All right, so I don't see any questions. So I'm going to move forward. Now we have the utility matrix, right? What are the different ways in which we can fill in the values of this utility matrix? So there are many algorithms out there. I'm just going to talk about two briefly. The first one is K nearest neighbors, or KNN. There are two types of KNN algorithms. One is user KNN and another is item KNN. User KNN uses similarity between user purchases in the past to recommend items. So let's say we have two people, Susan and Mike, and both of these people have very similar purchase history in the past. Both of these people have bought the same items or very similar items in the past. If Susan buys a new product, it would be safe to assume that Mike would also like that product because they have had a shared history of buying similar things. On the other hand, item KNN leverages the similarity between items to recommend. So let's say a person buys one type of Coca-Cola. It's safe to assume that they might be interested in buying another type of Coca-Cola, which is also bought by other people who have bought Coca-Cola, this type of Coca-Cola. Then we would want to recommend this to this person here. The other type of algorithm that exists out there to fill in these missing values is called matrix factorization. Matrix factorization is a more mathematically advanced algorithm, and I'm not going to go into a lot of mathematical details around matrix factorization, but I'll try to give a very intuitive understanding of this problem. So what matrix factorization tries to do is that it takes the whole utility matrix, the sparse one, and it tries to factorize it into two different matrices, such that the product of these two factorized matrices gives us the filled-in utility matrix. Okay, so let's try to understand what this means, right? you have your utility matrix, the sparse utility matrix to start with. What you're trying to do is factorize it into two matrices, U and V, such that the product of these two gives you the filled in utility matrix. What matrix factorization does, let's take an example of book recommendations. When you're trying to recommend books to people, what it does is that it tries to find latent factors that describes groups of users and groups of books together. Some examples of latent factors for books could be trying to group together books which have the genre romance, or trying to group together books which have based on the amount of action they have, or something as non-trivial as the amount of character development in a book can also be a latent factor. And each of these matrices U and V is representing these latent factors. So U here represents, like each row in U represents one customer, and each column represents the latent factors of books. And the cells here are filled with the inclination of a particular customer towards that latent factor. Similarly, for V, each column represents one book, and each row represents a latent factor for the customers. And each cell here is filled in with the likely inclination of that book to that latent factor of customers. So for example, if you want to fill in this green cell here, which has a question mark in it, it will be filled in by the dot product of the first row of U and the fourth column of V. I'm going to go a little deeper into matrix factorization and try to explain this a little better. Matrix factorization is traditionally a linear algebra technique that is used for dimensionality reduction. However, when it comes to recommendations, we don't really need to reduce dimensions, right? All we care about is filling in the missed values of the sparse matrix. So, like I said before, let each item be represented by a vector Vj, and let each user be represented by a vector Ui. Then the dot product of these two vectors is the expected interaction. Like I said, this question mark will be filled in by the dot product between this and this, right? Now, Vj and Ui, these can be found in such a way that the error between the dot product of these two and the actual known values in the utility matrix is minimized. So what we're trying to optimize here is this equation. We're trying to minimize the error between this known value 5 and the dot product of the first row of U and the fifth row of V. So if we have minimized this distance, then whatever we filled here should be close to the predicted value. Let's try to see sort of not a pseudocode, but just a flow of how matrix factorization works in practice. You start by randomly initializing U and V. By the way, K here represents the number of latent factors, and this is a hyperparameter which you can tweak. So we start by initializing U and V randomly. Then we see if the difference between the known values of Aij and the Vj Ui dot product is less than a threshold. If this error term is less than a threshold epsilon. If it is, then you stop, then you're done. Whatever U and V you have is a very good approximation of the original matrix A. If it's not done, then we update U and V using an optimization algorithm, and you go back to check if that condition is true. And then the cycle repeats until that condition of Aij minus Vj transpose Ui whole square becomes less than epsilon. Now, if you're interested to read more about matrix factorization and the math behind it and how it is implemented, etc., there are a lot of resources online, and I would highly recommend you to go and have a look there. I'll also post some resources in the comment section later on. Now, we talked about two approaches, right? One was KNN and one was matrix factorization. Let's see how these fit into our problem. So when it comes to k-nearest neighbors, when we talk about user KNN, what we're working on an assumption is that users who use the same services are similar. And that makes sense, right? If two users have been using the same kind of services in the past 1 or 2 months, then it's safe to assume that if one user tries a new service, the other is also most likely to do it. However, in case of item KNN, it assumes that services that are used by the same people are similar. The services are similar, which is pretty absurd in our case because we cannot say that GoFood and GoCar is similar or dissimilar, right? These are two independent services, and it's very hard to it's very hard to actually call them similar or dissimilar in any way. Another thing that did not work out in case of user KNN is that user KNN means storing a matrix of order n square into memory and computing it in memory, which would be very, very computationally expensive. So that is why k-nearest neighbors did not seem like a feasible option for us when we were building this algorithm. When we talk about matrix factorization, well, again, it works on latent factors of customers and latent factors for services. Even though latent factors for customers make sense and services doesn't make sense, matrix factorization actually uses a combination of these two to give you the final output. And that is why we decided to go ahead with matrix factorization as our final model for this approach. Now, let me talk a little bit about the challenges and finally come to what the workflow looks like. Again, I'm going to check if there are any questions. Okay, so I will be posting the resources of matrix factorization at the end of this talk in the chat itself, so you can read up over there. And in matrix factorization, how do you quantify the recommendation? Okay, so I'm not able to understand this question a lot, but how do you evaluate a recommendation system? Okay. All right. Okay. All right. So one question I have is, which one did you use to fill in the values, KNN or matrix factorization? I think I answered that. We're using matrix factorization in the long run. The next question is, how do we evaluate a recommender system? So how do we evaluate a recommendation system? Honestly, in real world, the only way to evaluate a recommendation system is by using field tests. There is no other way to evaluate a recommendation system to see if it is working in the real world or not. Or you can design your backtest in such a way that, let's say your utility matrix is built on 1 month's data, right? And we're currently in July. So let's say you build your utility matrix for May and then see what it predicted, and then you use those predictions to see if there were any conversions in June. So it's slightly tricky to actually evaluate a recommendation system, but the point is that you really need to run field tests in order to actually get a sense of how a recommendation system is working, and I will be coming to that as well in a bit. Okay, so these are some of the main challenges that we faced while building this algorithm. The first one was the size of the utility matrix. The second was the nature of the data that we had. And the third was choosing an optimization algorithm. So we have millions of active customers on a monthly basis. And we had over 30 service and payment combinations to recommend for. And if we try to include merchants, like GoFood merchants on it, it has a chance of exploding even further. So the size of our utility matrix was pretty huge. We started by using the Surprise Python library, and the training time that we were getting was around 6 hours, which was pretty large in my opinion, and it was kind of it made it difficult to do quicker iterations and try new things. And hyper parameter tuning was also becoming very difficult because of this training time. So we decided to try the Spark distributed environment with a Python wrapper on it, and our training time actually reduced from 6 hours to 1 hour. So this is how we dealt with the size of our utility matrix, by moving to a distributed environment approach. The second problem is with the nature of our data itself. Now, recommendation systems are actually built to predict how much a person likes or dislikes a particular item. That's what it inherently tries to predict. And in order to predict that, you need some explicit feedback data, which is, for example, ratings given by a user on IMDb or Netflix, or even on, let's say, Zomato or Swiggy. You have an option to rate restaurants, and that is explicit feedback. You're explicitly telling the service that, hey, I like this movie or I don't like this movie, by giving it a less rating. However, we don't have this data. What we have is implicit feedback, which is like the transaction history of a person, or the click patterns of a person, or the search history of a person, or how many times the person has used a service in the past 1 month. So what we needed to do was convert our implicit feedback into a preference score, or explicit feedback. Now, again, there is a lot of math involved here, so I'm not going to go into details of how we made this conversion. There is a reference link right here of the paper that helped us figure this out. So please feel free to have a read. I will also post this on the chat after the presentation. Another challenge that we faced was picking an optimization algorithm. Now, we had two options: stochastic gradient descent and alternating least squares. Both of these are algorithms used to optimize a cost function. Even though stochastic gradient descent is most widely used, ALS is recommended for implicit feedback, and especially in a distributed environment. And implementing stochastic gradient descent is not very trivial when it comes to a distributed environment. So that is why we decided to go ahead with the ALS optimization technique. Now, this is what our final workflow looks like. We get our data, raw data from BigQuery. We perform some ETL on it using pandas. Now, performing ETL from raw data to make it into a utility matrix was not very computationally heavy. And pandas was doing a great job with it. So we went ahead with that. Now, once we have the utility matrix, we feed it into the Spark ML library. And that library spits out the filled-in utility matrix, from which we can infer the list of customers to target. So this is what our workflow looks like right now. And we are currently training this model on a weekly basis, because it is recommended to train this model on a weekly basis, because that's the pattern that we have seen, that's how much time it takes for the data to shift. So it makes sense to train it on a weekly basis. Now, once we had this model in place and it was giving us decent backtest results, we wanted to see how it would work in the real world. So we designed some field tests for that. And this is what the experiment design looked like. We have our entire, so let's say we pick a service to test. Let's say GoFood. Again, let's take the example of GoFood again. We want to test for GoFood, and we have the population of all the people who've never used GoFood, which is our base pool. We extract two groups of people out of it. One is the control group, which is n randomly selected customers, and one is the test group, which is the targeted set of customers that our recommendation engine is telling us are most likely to convert. We give the voucher to both of these sets, And we measure the conversion rate on both of these sets. And our hypothesis is that the conversion rate of the test group, which the recommendation engine is suggesting, would be much higher than the conversion rate of the control group, which is a random set of people. And luckily, we got the uplift of between 5 to 7x on the base conversion rates across service types. So this kind of proved that, yes, our model was doing what it's supposed to do. We are able to get an uplift, a pretty good uplift on our base conversion rates. So yes, that's it from me. The key takeaways from this talk are that we were trying to build a cross-sell targeting model which solves two problems at once. One is that given a service, you get a list of people who are most likely to cross-sell into that service. And the other is, given a customer, you give us the list of services that the person is most likely to transact with next. And this model gave us an uplift of around 6x on the current conversion rates. That's it from me. Thanks a lot for attending. I will be around on the chat section now to answer any questions that you might have. Okay, so I see a question. How much data is ideal to get a fairly good recommendation system? That's a very subjective question, but it's difficult to put a pinpoint saying that, okay, I need X number of data points to get a fairly good recommendation system. But in general, recommendation systems are built, will have very sparse data, right? So it makes sense if you have a fairly large amount of data with you. You have somewhere in maybe more than 100,000, ranging more than 100,000, at least on the customer side, if not on the item side. So because it's a sparse matrix, the more data you have, the more data points you will have. So yeah, it makes sense to have a fairly large amount of data for you to build a recommendation system. I'm going to stop sharing my screen and I'm open for questions if there are any more.
Guys, if there are any questions, posted in the comment section so that she can answer it. Gunjan, I have a question.
Yeah, sure.
So you all have used collaborative filtering, right?
Yes.
So you give a thought to content-based filtering as well, like considering both of them together for targeting the new audience or the new products, possibly collaborative filtering, but then retaining the existing ones using the content-based filtering.
So, okay, so for us, content-based filtering did not really make sense because we don't have any profile. So, okay, essentially, content-based filtering works on user profile and item profile, right? You need to have some properties or characteristics of items and users in order to leverage that for content-based filtering. We don't really have that. So, there's no such thing as an item profile for a service. Right? It's just a service that people use, and it is just, okay, if you can book a car using this service, that's the profile of that service. And even when it comes to users, we don't have any demographic information about our users. We just have their transaction history and how they have interacted with our system. So that is why content-based filtering did not really make sense for our use case. And this particular model was specifically built to retain existing users and to make them cross-sell into using more and more services. It was not really intended for brand new users. The user has to be at least 1 month old on the platform. I will be posting. I'll just later in the comments of the video, I will post some references for matrix factorization and the paper that we have used overall.
I guess we don't have any other questions. We'll still wait for 2 minutes if there are any questions. So There's a question.
Yeah. In the book, so the question is, in the book recommendation example that you used, how do you numerically measure the likes or dislikes of customers to represent in the recommendation utility matrix? Okay, so it depends on the kind of data that you have in the original utility matrix. If in the original utility matrix you have the ratings given by these users in to the books, then what you will be predicting will also be ratings. So that is the numerical measure of likes and dislikes. Suppose a person has given a rating of 2 or 3 or 4 to a book. That is a numerical measure of a like or a dislike of a customer to a book. And if a rating has a range between 0 to 5, then your predictions will also have the range between 0 to 5. And that's how you numerically measure likes and dislikes. You can set a threshold. Say that if someone has given a rating more than 3, then I'm going to consider it as a like. If it is less than 3, then I'm going to consider it as a dislike.
So Gunjan, one more question from my side.
Yeah.
Uh, you mentioned two algorithms, right? SGD and ALS for reduction of the cost. So how much was it reduced? Like the time complexity? How much was it
The
reduced?
time complexity was actually reduced because of us using a distributed environment. The optimization algorithm choice was not really to reduce or increase the time complexity. It was more to figuring out which algorithm makes sense in a distributed environment. So for us, alternated least squares made more sense in a distributed environment. That's why we went ahead with that. So there are two questions. Wanted to know from a product manager point of view, how many people are in a team for this project and how long is spent on the research. Okay. So, okay. So from a product manager point of view, if you look at solely from the data science perspective, um, it was just me when we started, and then one more person joined as a data scientist for this project, and it took us on the research part, it's quite difficult to quantify just the research part because it's an ongoing process, right? We tried the classification first, it worked out, but it was not scalable. So we went back and did more research, and then we thought of recommendation system. We also thought of other ways. We were also exploring other things to figure out what we can do. So it overall, I think 6 to 8 months is a decent time to think of from the very start of the problem till you reach a point where you can actually use it in production. This includes research, this includes everything else.
Okay, so the question is, how many models were tried before you guys arrived at the final model, apart from the ones those are discussed?
Okay, so the classification was actually the first model we tried. After that, in classification itself, we tried multiple models, like we tried SVMs, we tried tree-based models, etc. After that, I think, also tried to explore Markov chains and that side of things, but that didn't really make sense for us here. Within recommendations itself, actually, we tried a lot of different models. I mean, how many models? I think I would say 5 to 6 models were tried, other than the ones that were shared here. Because within recommendations itself, to actually conclude on matrix factorization, it was a pretty long journey.
Another question we have is, which optimization algorithm did you use to evolve the utility matrix?
Yes. So like I said, we use the alternative least squares optimization algorithm. So I discussed two methods, right? So we started off by using the surprise Python library that by default has the stochastic gradient descent optimization algorithm. So at that time we were using that, but when we moved into the Spark distributed environment, we started using the alternative least square, and that's what we're finally using.
So we'll wait for a few more minutes for any other questions. I guess we don't have any other questions. So let's wrap it. So Gunjan, thank you so much for joining in and thank you for accepting our invite. It was a really great session. We enjoyed a lot. It was very helpful. Learned a lot of things. I hope that the viewers have benefited as much as I did from this talk.
Thank you so much for inviting me. It was a great experience. It was slightly weird because I'm talking to a laptop screen. It's a pretty new experience, but it was great, and I hope to continue this new relationship and give more talks with bits in the future.
Sure, sure. Looking forward to that. Thank you so much.
Thank you. Bye.
Bye,
Thanks
everyone.
everyone for attending.